Negative properties are those characteristics of matter which are affected by a solute being dissolved into the solution. And so one of them is called the vapor pressure. And this would be, as it sounds, you have a container and there's like a pressure gauge on it. And in here you have some liquid. Let's say this is ethanol, which would be C2H5OH. It has the OH ending, so that means it can have hydrogen bonds. And some of this ethanol has some more energy than other particles. And so some of these particles are able to escape up into the air. And so they bounce around and they hit the pressure gauge and they cause the pressure gauge to say there's a certain amount of pressure, the force per area on that pressure gauge. Now, if you go and put a salt or some kind of other solute, the thing that gets dissolved, right? A salt in here, you can literally put like table salt if you want. Then what that does is it acts like little magnets. These are ions, and if we have ions and something which has these specialized dipole-dipole forces, hydrogen bonds, right? Then they act like little magnets. They connect together. And so then the ethanol is held into the water by the dipole-dipole forces, and it's ion dipole when these are held together. And so some of this ethanol tries to escape, but the sodium or the chlorine holds it back. So it takes more energy to be able to cause that to escape. And so what ends up happening is the vapor pressure will be lowered. The vapor pressure will be reduced because there are fewer particles able to escape. More of them are held into the liquid phase in the solution because of the ions. So the ion dipole forces hold the ethanol back, keep more of it from evaporating. Another colligative property is the boiling point elevation, which means to raise, to elevate it. And so this happens in a pot of water. So we have some water in the pot here, and we have a little fire. And so some of the particles gain enough energy, and they can go off at 100 Celsius, and they can boil away. Now, if we go and add a salt to this, then we have, again, H2O, which has the OH part, so hydrogen bonding can occur. And we have some sodium ions and some chlorine ions. And we're going to end up again with some ion dipole forces. And when these forces are created, then we hold back the water molecules. So fewer of them can escape because there's not as much energy, or it takes more energy for them to escape because the salt is holding those water molecules back like little magnets. So since the salt stays in the water, the more water is held back in the salt. So you have to go and heat this up even higher to be able to get those water particles to be driven into the gaseous state. So the boiling point has to be raised, or the boiling point is elevated. And a third one is freezing point depression, or to lower. And the freezing point is depressed when the salt ions interfere with the formation of the ice. For water to form ice, we have to cool the particles off, slow them down, and then they have to form this nice little arrangement with all those hydrogen bonds which form here. The hydrogen bonds which form this little hexagon-like shape. Now, if a salt comes around, let's say this one's calcium chloride, that's typically used on the roads. One of the reasons that this is used on the roads is it's more environmentally safe. Another reason is it breaks apart into three pieces. So instead of just having Na plus and Cl minus, this breaks apart into Ca plus 2, Cl minus, and another Cl minus. So more pieces means more disruption because each of these can come along here and disturb these hydrogen bonds. And so more pieces of ions that break apart, more disruption. And so that's why calcium chloride is a favored salt in this particular use. So then what ends up happening is when you break these connections, the water molecule is free to become a liquid again. It floats off. and you have to remove even more energy to get it to slow down some more to be able to lock it into place again to make it ice again. And so the freezing point gets lowered. So you can be outside on a minus 10 Celsius day and still have liquid water on the road because the salt is added to the road. And even at a below freezing temperature, you have liquid water because the freezing point can be depressed to, let's say, minus 15 Celsius. So it has to be even colder for the ice to form. So we can put that into use and figure out by how much does the freezing point get depressed or the boiling point get raised. What we need to know are a few items here. One of them is the molality. So I'm actually going to go and look at that in a second. The molality, not to be confused with molarity, the molarity is the number of moles of the solute divided by the liters of the whole solution. The molality is the number of moles of particles. And so it's important to look at that and realize that we're not just talking about like the solute, we're talking about how many particles the solute forms and looking at that in moles. And these generally are going to be atoms or ions, or they could be molecules. Not going to be formula units in this case because formula units would either break apart into ions as they dissociate and separate, go their separate ways, or they just would not even dissolve. And if they didn't dissolve, then it wouldn't really be a concentration problem that we want to look at because they're not dissolved in the liquid. And we divide this by the mass of solvent. So the mass of solvent. This is not the solution. This is just the portion which is doing the dissolving. And this has to be expressed in kilograms. And it's typically water. When we do our examples, we're going to be looking at a salt or some kind of material dissolved in water. So we're looking for how many kilograms of water do we have. Okay, so we need to know the molality. That's one of the first things we're going to look for. And we can do problem here. Let's find one that has multiple pieces. Okay, here we go. Here we have iron nitrate. When iron nitrate dissolves into water, we have, let's see here, iron plus 3, so iron Roman numeral 3 nitrate. We have 4 pieces that will actually break apart and dissolve in the water. So if I had 1 mole of iron nitrate, that would be formula units, and this dissolved, I'd end up with 4 moles of ions. And you can see that I hope that that occurs because we have 1 iron and 3 nitrates for every single iron Roman numeral 2 or Roman numeral 3 because it's plus 3. For every single iron Roman numeral 3 nitrate that dissolves, 4 moles of ions will form because the iron plus 3 and then the 3 nitrate minus 1s will all go off their separate way. So we are looking at 4 moles of ions for every 1 mole of the formula unit. Now it tells us how many grams of this material we have. We need to convert that to moles. So then we look at the 23.64 grams of the FeNO3 and we know that, let's see, Fe is 55.85. There are 3 Ns, so that's 14.01 each. And there are 9 Os, so that's going to be 16.00 times 9. So 241.88 grams of FeNO3 for every 1 mole. So how many moles do we end up having? We have 23.64 divided by, it's going to be about a tenth, right, or so. So 0.1 would be the estimate, and we have 0.0977. So pretty close to 0.1, and that's how many moles there are. Now this is moles of FeNO3, which breaks apart into 4 pieces. And that's what we're really interested in when we're looking at the molality. So we're going to multiply that by 4. And so then we're going to end up with 0.391 moles ions. So 0.39 moles of ions is what's dissolved. That's the number of moles of particles in the solution. And to find the molality, it's the moles of ions divided by the kilograms of the solvent. This is grams, so it's going to go deci, hecto, and then kilo. So 0.3311 kilograms of the solvent. So if I divide by 0.3311, that gives me a molality. The molality is lowercase m. The molality equals 1.18. And that's going to be in moles per kilogram. Okay, so that is needed because we want to know how is the solution affected by the particles dissolved in it. And the molality will tell us that. What ends up happening is the boiling point is increased, the freezing point is depressed. So to determine that, we look for the change in the boiling point. And the change in the boiling point is determined by multiplying a constant for each and every different type of solvent we have times the molality. And for water, this constant is 0.5120 degrees C kilogram per mole. And for the freezing point, which is depressed, the change in the freezing point, this is delta or change in the freezing point is equal to a constant for each and every different solvent that there is, a different constant, times the molality. And so for water, this constant is 1.860 degrees C kilograms per mole. And so if I take the molality now and multiply it by the constant, I get the change in the freezing point. And so the constant 0.5120 degrees C kilograms per mole times 1.18 moles per kilogram, you can see that the moles on the top and bottom, kilograms on the top and bottom, gives me degrees Celsius, which is the change in the temperature. So this is not the actual new temperature. This is the change in the temperature. And so 1 times 0.5120 basically would be like 0.5120. It's a little more than that. So multiplying that, you get a change of 0.60453, so 5 degrees C. And so the boiling point is elevated or raised 0.605 degrees. And the freezing point, so times molality, 1.18 moles per kilogram. And so this crosses out moles and moles, kilograms and kilograms. And the freezing point is depressed even more so. And you end up with a temperature change of 2.19, and we can have only 3 sig figs, so we're going to round that up to 20 degrees C. So then this asks for what is the new freezing point? What is the new boiling point? Don't enter in these values. What you want to enter in is what the actual new points are. And so the freezing point for water, because all of this stuff we're talking about in this drill is aqueous, so it's all going to be in water, right? In water. The freezing point of water normally is 0 degrees Celsius, so we're going to depress it and make it 2.20 degrees lower. So of course this will be negative 2.20 because we're going to subtract from 0. And the boiling point of water is normally 100, and we're going to elevate it by 0.605. And so this will be 100.605. And you can go ahead and have all those decimal places because the original value of 100 is 100.000. You can consider it to be a correct value like that. So that's the new boiling point elevated from the old one and the freezing point depressed from the old one.